All right, so we're going to start with Homo-Mandel experiment. Homo-Mandel experiment is a landmark experiment in the history of quantum optics. And to motivate it, I would like to first ask you what you think about our quantum optics lab. I mean, you have done a few, maybe 3 sessions, and you guys have done all of it, I presume. Do you feel like there's anything in the experiment that makes you convinced of the presence of photons, the particle nature of photon?
I'm thinking you're asking about, oh, is there any blizzard about this experiment?
There's a what? A visual?
Unpleasant about this experiment.
Unpleasant? Unpleasant. I of course there I can relate with that, and but I like from my experience, because I've also run those experiments myself. My feeling is that I have not yet seen an experiment that convinced me of the presence of photons, the particle nature of it.
But even the GRA experiment, like we detect simultaneously this photon, which only happened if it's the particle nature, if wave nature.
Right. Yeah, the gating experiment, right?
Yeah.
Yes. That's why I asked you guys to do with both classical source, light source, and the quantum light source. With the classical light source, you see that when the flux rate is low, you also don't have much signal coming through because the gating signal is just simply too weak, right? So to produce a zero coincident count in such experimental setup, I think it's not too hard. You just need to have a light source that's weak enough to not trigger the gating signal efficiently, and you will have low coincidence. So for me, I feel like maybe there's still a loophole somewhere. That's why I asked you guys to do all 3 light sources to compare them. All right. We try to add.
You mentioned like do not get detect.
Mhm.
Trigger the gate properly, but I think it's not the correct flavor.
Right. Of course, you need to trigger it to see the single photon nature, but that is more of like a background suppression, a technique for background suppression than like any to stimulate any physical process. You see what I'm saying? I feel like the gating is a technique to suppress background. And if you suppress it enough, then sure, according to the theory, the single photon signal will stand out. But I'm just saying that, of course, that is the standard interpretation. That's the standard thing to do. But like I said, as I said, the original GRA experiment is pretty straightforward and simple. The GRA experiment that we do using SPDC source, there's complication involved, and like I said, when you pump this at different levels, the signal might not be as what you think it should, right? So there was like a lot of parameter control involved during our experiment, right? So I keep having this feeling that we really need to do something that shows the particle nature of photons, and that's why we try to add this landmark Homo-Mandel experiment. but unfortunately, we have tremendous physical difficulties so far, and we have not yet succeed in building it and demonstrating it in our lab. But today, I want to start our discussion with this experiment, just to understand this experiment conceptually, to see why this is sufficient to show us the particle nature of light. Okay. All right. So in our lab, we have the alignment laser, right? And the alignment laser is basically a beam splitter, right? No, sorry. The alignment laser plus something called acetone. So this is our laser, and this is 633 nanometer. So it sends light to something called acetone. It's a prism that is made to split the beam. So it's basically a beam splitter. Split the beams symmetrically, right? If we take one light source and send it to an interferometer, right? So let me just mark it like this. If we take it and send it to a beam interferometer, let's see. So microsecond interferometer, right? And detect it at one port. What do you see? We see an interference fringes as we move one of the mirrors, right? So we see interference fringes. When we do this with BBO, so this is essentially a single photon SPDC source. Okay, so this is also laser for 5 nanometer. Also get 2 beam out. Okay, supposedly we have a single photon. Okay, so let me write like this. And we send it through the same interferometer. What do you see? You also see interference fringes, right? So they are the same. Can we do something that show just like complete different signals without additional? I mean, if I hide this in a big block box from you, right? Can you distinguish the light source? Well, with this measurement, you cannot, right? And of course, I said it before, because such a measurement does not involve the photon operators in it, so they cannot distinguish different photon statistic. That's correct. So we ask ourselves this question: is there really no way to distinguish a single photon source and the classical coherent source using interferometries? Do we always have to do correlation measurements? Well, in Hong-Mandel experiment, they did a little modification. They have a little modification from what we have here. So let me start with this. When you have light that go go into two detectors. What do you see? In terms of coincident counts, you see a flat line, right? Uncorrelated. Now, let me ask you, if you do it like, if you put a mirror here, be careful with the drawing. Okay. This is a terrible drawing. Okay. If you put a mirror and a beam splitter, right? And this goes to here. This goes to here. Does it change your result?
Is it a mirror so there is no black light, right?
Yeah. It's fully reflective.
Yes, there should be.
Should there be any difference in your result? And what difference do you expect? What difference do you expect? Well, I don't expect any difference because, I mean, light like a split is still light, right? So you have one being split like this and the other being split like this. And of course there is cross turns. Yes? Okay, so you will see, sure, you will probably see, so here. Let's see. So suppose the intensity is the same. Previously we see this. So detector 1. Detector 1. Okay, so this is detector 1. This is detector 2. Okay. We see detector 1. Previously we see detector 1 as like a line, right? And we see also a flat line in the coincident counts in the correlation measurement. Now with the implementation of two mirrors and one spin splitter, sure, we probably will see if there is a little phase difference, we'll probably see a higher level of light, right? Or a lower level of light. But if we don't move it, it should stay as a flat line, right? But for coincidence counts, I'm still expecting to see a flat line, okay? Because what gets in here is just, it's just the same coherent state, but with a different amplitude, that's all, right? So intrinsically, there's really not much difference. However, if you do this, let me see. Let's see. If we have a different source, then of course we expect to see a bump, right? Because they are created in pairs, right? So they will arrive at the same time, right? Okay. Well, yeah. Anyway, so there's supposed to be a positive correlation, okay? Now, when you do this, okay, what do you expect to see? Huh? Zero? No coincidence. Why is that?
It will be either or, either both going to same detector. That's the impedance.
Why? Why can't you just have one going this way and the other going this way? I mean, that's also possible, right?
Yeah, but 2 times opposite with opposite sign will be.
How do you know 2 times of opposite signs?
When you are doing that one expanded
Huh?
for the single photon.
Okay.
I think maybe you want to mention about the beam splitter when they polarize in the beam splitter. And there is maybe he mentioned about the phase difference. That what you mean?
No, both will be same phase. So
On detector D1, on the single detector, I mean, this is really just the same as this interferometer, right? So the behavior should be identical, right?
in D1 it should be.
No, if we do not modulate, this is if we modulate. If we modulate the mirror in time, right? If we modulate the mirror in time, yes, it will oscillate. But if we just keep it fixed, then it will stop at either a high value or a low value. Okay? It will remain there. What I'm trying to say is, from the interferometrical measurement, it looks like we should get the same result. So if you have the delay that is set up to cause, maybe like a pi phase shift, then you will expect to get a lower signal, and if the phase shift is constructive, you will expect to get a higher signal. So it should be identical to the coherent laser measurement. Okay, but what about this? Well, here, intuitively, we think there are several possibilities, right? We could have this photon get reflected from this, from the beam splitter, and the other photon go through the beam splitter. So here you can have 2, 0. So the first place indicate this port, and the second place indicate this port. Okay, so this is just mode labeling. Okay, so we're expecting this, and on the other hand, here we're expecting this. Okay? But we also think this should be possible, right? One go through, the other get reflected.
Yeah, but the means yes, that is possible, but there is like that is possible in two ways, right? Like the first one get reflected and second one to get transmitted.
Yeah.
And the other way.
Yeah.
So it's
So there are two ways.
Opposite will come.
How do you know it's opposite?
Because like it has both has a phase of phase difference is fine. Right?
How do you know?
Because it's like getting translated and reflected. So that
can it be positive?
These both should happen, but
Mhm.
these both should cancel.
Well, if you have not read any quantum optics textbook, would you expect the sign to be opposite?
Because beam splitter is like A plus B into A minus B, right? And since these are two independent states,
what is the reason? What's the physical reason for that? You keep telling me textbook results. I don't want that. I can read the textbook myself. Others can read textbook themselves. I'm asking you, if you give me this answer, do you have any insight to already know that there are going to be a phase difference before any further discussion? Like, just given what we have here, do you expect the phase to be different? I don't know what it would be. Maybe positive, maybe negative, I don't know. Okay? But intuitively, I think, like I said, intuitively, I will expect that there are all these possibilities. And like he said, there are indeed two possible ways to get one photon here and the other photon here, which is, so we can get this photon reflected to this detector, and this photon reflected to this detector, or we can have this photon transmitted to this detector, and this photon transmitted to this detector, right? And of course, the photons are indistinguishable, so these two processes are also indistinguishable, okay? But I don't know about the phase relationship. I don't know any of that, okay? What I'm saying here is that what I see here is that I think the two ports should have like identical signals, and thus I wouldn't expect any. Just like before, they have identical signals. Here, when I change my measurement schemes, right, just like reroute the photon path a little bit, I would expect that I would see the same signal as before, okay? And of course, this will be, sure, I give you that. So when you have these things, one going here, one going here, you have the same positive correlation as before. And if you have this, then you have negative correlation, right? So you don't get two clicks at the same time, right? Either one click or the other click. They don't click at the same time. So I would expect this. Okay, so maybe I do expect a little difference. I expect two different contributions, and I expect that my data will be like a mixture of both, and I expect that eventually I'll get this. So maybe going from a positive correlation to an uncorrelated, like a flat correlation. That's what I would expect. Okay? So if I have a click here, when a click here occurs, when they both click at the same time, then I have a count in the coincidence, right? But if they don't click at the same time, then I have no zero coincident counts. Therefore, you have a dip. Okay?
How about 1, 1, 1, 1, 1?
1, 1, 1, 1, 1 means one go here and the other go here.
Yeah,
They click at the same time.
Yeah.
Right, so that gives this.
Okay.
Okay, so this is what I would expect from 1, 1. And this is what I would expect from 2, 2, 0. So I expect both signals should be present in my detector. And as with time averaging, I should have a flat line. That's what I would expect. Okay? So maybe yes, with such a setup, we can see a different result between the coherent laser and the biphoton source. All right? Now, so without further discussion, it seems like such measurement schemes although we're still using coincident countings, okay? But we're not gating or anything or doing anything like that, okay? And it seems like it might be possible to use such a measurement scheme to distinguish between the coherent light and the biphoton source, okay? And this is the experiment that Hong Wu Mandao did. So there are 3 persons. I think Mandao is the advisor. Okay. So what they find when they did this experiment, they find a result that is actually, so this is what we expect, right? They find a result that is even more surprising. They find this. So instead of a flat line, so the classical light give us this flat line. Oh, right, actually. Let me come back to here. If we do have a flat line, right, then this cannot then such measurement cannot distinguish between the classical light and the biphoton source. Okay, so yeah, so this is the classical result. But anyway, when they did the experiment, they found that there is actually a dip instead of a flat line. And they give an explanation for this phenomenon. And this explanation involves 2 photon states. Okay, interference between 2 photon states instead of interference between 1 photon state. So the measurement that we did with the microcenter interferometer, that is interference with 1 photon state. And that does not have a different result than the classical, than the coherent light. But the interference in the 2 photon state can give a different result. Okay. So, so their result was seen as like a smoking gun experiment to prove, to show that the light indeed exists in the photon states. Because when you think about it, if you just have the classical light, the coherent laser light, there's no such things as, I mean, forget about all your quantum optics learnings. If you just think about the coherent light, the classical coherent light, there's no such things as two photon states or one photon state. There's no such things as photon states, right? So like the existence of photon states needs to be shown, and such a measurement shows the difference. Okay. And this is, here I'm gonna give a quick derivation for its explanation, and that involves. So it turns out that the beam splitter is a device that couples modes from different, how do you say? So you have mode from here and here, right? And
What do you mean different mode?
yeah, that's a good question. Different mode. Usually we define mode by k vector, right? So you feel like this and this are the same mode. Yeah. Okay. That's a good question. I don't know. Okay. But through this experiment, they found that okay, maybe I can say this. This mode, the reason this mode and this mode is different is because when light goes into this material, it scatters or it regenerates, right? So when it regenerates, then that is considered a different mode. Okay, maybe let me start with that. Okay, so this is, so the source, so this mode, the source is from your light source, but this mode, the source is from this material. Okay, on the material. Let me give labeling to this mode. This is labeled as 0, 1, 2, 3. Okay. So what they found through this experiment is that a beam splitter is a device that couples different modes. And so you can see this as like input and output. That couples different modes. And after the coupling, the operator commutation relationship needs to be maintained. Agree? So what does that mean? That means A1, A0, A3, A-3, A-2. Before we have A0, and A0, that is 1, that's 0, right? And A0, that is 1, right? And we have between different mode. So within the same mode, if you have dagger, that's 0.
Different mode, everything will be 0.
Yeah, and raising, that's 0. Lowering, that's 0. But if you have raising and lowering, that is 1. But between different mode, it is always 0. Yeah? Okay. So they found that the beam splitter is a device that couples different modes, yeah. And in order for the creation and annihilation operator to maintain the quantum mechanical property, so because this is the quantum mechanical property, right? This ultimately has to do with the quantization of light. Remember? When we talk about quantization of the E field and the B field, it all boils down to this, right? So in order to maintain the quantum property, the commutation relationship needs to stay intact. And because so generally you can assign like transmission coefficient and reflective coefficient, and there can be complex number because not only the amplitude is splitting, you can also attach a phase to the reflected light. So there's that. And so in principle, the coupling could have like different coefficients. Okay? There are 4 possible. So from this side, you could have refractive and transmissive coefficient, and from this side you can have a different reflective and transmissive coefficient. And in principle, they can be complex numbers. So there are 4 of them, and each one has like real part and imaginary part. So you have in total 8 parameters, 8 free parameters, yeah. But because of this photon commutation relationship, so this is like before the beam splitting, and after the beam splitting, of course, you are expecting them to stay the same, right? So, for example, 2 should be 0 and 1 and 2 and 3. You're expecting this, right? I mean, they should just have the same properties. Between different mode, the commutation relation is 0. Within the same mode, it is 0. If it's the same, it has the same form. But if you have raising and lowering, then it's 1. So anyway, so this quantum property of light restrict the property of the A parameters, and all boils down to like an equation. And for the reflective and transmissive coefficients on both sides to satisfy this communication relationship, there are different combinations. One of them is this. So this is basically a pi over 2 phase. Okay? Right, so assuming this is a 50-50 beam splitter. All right? So this is one of the possibilities. There are other possibilities. Okay, but let's start with this. This gives you that okay, so just a little bit of algebras. Why do we wanna express 0 and 1 in terms of 2 and 3? Because we start in the Hong-Mandel experiment, we're starting with one photon here and one photon there, right? So that is a state described by this, right? So 0 and 1 denote the port, and 1 means one photon, right? This state can be written as this. Okay, this is just the vacuum state. Okay, and vacuum state is basically 0, 0, 0, 0, all of them are 0 for 0, 1, 2, 3, all the modes. Okay, so this is just like a shorthand of a lot of zeros. Okay. To see how these states transform after the beam splitter, we must replace the creation operator of the 2-port by the racing operator of the other 2 ports. Okay? So that's this. Yeah? And you can carry out the expansion. It looks like this. Okay. Then you have the operators operating on the state. Okay? All right. Now, we see that here the imaginary number result in this minus sign here, right? And that gives a phase difference between these two photon states. Therefore, these 2 photons, they cancel. Yeah? Okay. Now we can track using, sorry, this is plus plus. we can track what these states represent. So the two here give you 1 photon here, right? And this 2 comes from this. Yeah, and this comes from this. Okay, so what that means is here you have 2 coming from the 0 port, and 3 coming from the 1 port. Okay, so these are the direct transmissive process. On the other hand, here the 2 comes from here. The 2 comes from the 1 port. Okay. The 2 comes from the 1 port, so that's this process. And the 3 will come from the 0 port. That's this process. Okay. And this 2 process has the opposite phase, and they canceled. Okay. Now, if we ponder about this result, I think there are 2 things that, yes.
To make sure why there is a phase, you use a red pen to point the
Yeah. So in principle, this could be any number. Like I said, there are 8 parameters, and these 8 parameters are restricted by the photon communication relation of the field operators.
some kind of, I just meant is a constraint. So
Yeah.
a parameter follow this constraint.
Right.
Get the result like that.
This is one possibility,
One
right? This is one possibility.
It's also possible like A0 plus A1 and A0 minus A1 type.
That's another possibility.
Without going
That's another possibility. Okay. All right. Although with that possibility,
I think it's still,
you would still have
Yeah.
a minus there.
yes.
Yeah. Yeah, but you will have, okay, sure.
There
Yeah.
won't be any I,
Yeah.
but the
Yeah.
minus will be.
He's saying that, how about 0 plus A0 plus A1, A0 minus A1? Is that a possibility? Yeah, looks like it could work. Yeah. Anyway, there is like, so if you go to a quantum optics book,
Only difference will be that in the second stage, it will be minus sign.
yeah.
It's 2,
In-
0,
yeah.
minus 0, 2.
Yeah,
Or can you just list some, I mean a few of them?
a few of them.
Yes.
I don't know. I need my book. There is, so my favorite quantum optics book is by Jerry and Knight. And there is like this general equation that give you exponential I, phi, exponential theta. So they use phi and theta as parameters, and there are just like a lot of possibility. Okay, so I strongly recommend that if you want to have more examples. But like he said, plus and plus 1, so 1 plus 1, 1 minus 1, that seems to be working too. Okay? All right. But the point that, okay, so these are just like technical details. Let's focus on the physics. I think there are two things that are interesting to us here. Okay, first of all, this is a phase difference between a two-photon state. Sorry, not a two-photon state, not in terms of two photons in the same mode, but it's more precisely, this is like a two-mode state. Okay, so single photon in two modes. And I think the fact that there is the phase exists, like there is like a interference, like there's a destructive interference exists between such two mode states. That appears to be. Do you feel like there's no classical counterpart to this?
Actually, I think the way you mentioned about destructive interference is already involved the Binslitter properties.
Right.
Yeah.
Yeah.
It's like the phase shift in the
Right.
reflection of the
Yeah. Okay, so you're saying, yeah, sure. I feel you feel like having a destructive interference is not a biggie, right? It's not like too surprising because if we just think intuitively, the beam splitter introduced some kind of phase shift, and it combines beams. So sure, there should be some kind of interference occurring, and this picture, we can also draw this picture for classical wave, right? Yeah. So maybe the interference between these two are not too surprising. Okay. Sure, I give you that. How about the other point? Another point is that I think that the point, sure. So if we don't focus on this part, let's focus on this part. I think that the other pore, one pore is completely depleted. The fact that the other pore is completely depleted, that is a result that does not show.
Classically, reflection will not change phase, right? Classically, a reflection will not change phase. Right?
It could.
When you use a mirror, you
Yeah,
don't
it could.
It add phase?
It could. Yeah. The coating can have certain properties such that it does that. Yeah, that's no problem. For example, you can have like a multi-layer dielectric mirror, okay? And the reflection is by interference between different layers. So your output light could have a phase difference from the input light. So that is possible.
Yeah, but that's because of the path length, right?
Yeah, but I'm saying that to give like a reflection, a reflected beam, a phase that is a phase difference from the input beam that is possible for the classical light. That's not unique to quantum property.
Like, in sense of like if there is a addition of like the addition in the path length.
A broad picture is, for example, you go from the less, it's like a string, right?
Like an oscillator?
Yes, or just like a string. And when you have like a very dense density, when uh, when you shot this, it will the wave when it's reflect back. I mean, because you go for example. Oh, okay. Uh, the correct word is about the reflect, refracting. Uh,
Refracting? Refraction?
uh, wait.
Yeah, I know refraction can add some phase, but if
It's-
it's like a
When
reflection,
you come when for example the light from the less refresh refraction. I mean.
Yeah, refract. There's reflecting and refracting. Refract means
Yes,
the angle changes a bit
Yes, I mean
in the
about
transmission.
How you call it?
Reflection?
Yes.
There's
I mean,
reflection
refractive index.
refraction.
Refraction
Yeah,
and
index.
refraction.
You come from the less refraction index to the higher refraction. You will get the reflection.
Index of reflection.
I mean the fact in that
Yeah,
condition.
that I understand, but
Oh, he's talking about Fresnel's
I'm
equation.
talking about reflection, like if it reflected at the same
Yes.
angle, the refractive index doesn't change.
Reflection. You mentioned reflection.
Reflection.
But reflection property depend on refraction properties.
So you're talking about
example,
going from one media to the other media.
Yes.
Yes, you
So
have the
yes,
transmission and you have the reflection, right?
Yes.
And both could pick up a phase according to the Fresnel's equation.
Yes.
That's what you're talking about, right?
Yes.
Yeah.
Yes.
Yeah. So depending on your wavelength, right? And your angle.
Actually, depend on the
Is-
refraction index and also the correlation.
Okay. Right. Anyway.
But that
w-
phase
you-
is between R and T, right? Or incidence and R.
Yeah, but this result is between R and T, like a cross product between R and T. Okay, what's the question here?
He is not there is no phase shift when the light reflects back from the insulator.
There could be. I mean, the fact that you have a -1, that is the phase shift right there, right? Anyway, the phase shift is not a quantum property, all right? So that exists for classical wave as well, right? But let's just look at the fact that, okay, that's not, like you said, interference exists in classical wave. So without going into much technical theoretical details, this result would not surprise you. Yeah. I agree. Okay. But how about this? What surprised us is one port is completely depleted. One port is completely depleted.
So they go together to the same direction after.
Right. Yeah. If there's no photon, right? If there's no photon, if photon does not exist, we only have classical wave. You cannot have one port completely depleted. Of course, you can adjust.
We can have
You
a
can
phase such that
adjust a phase, right? But it's not gonna work for all mirror positions. But this works for all mirror positions. It doesn't matter how much your delay is. Okay? It doesn't match. It doesn't matter how the phase difference between the two ports. You always have 0 on one port. So the fact that you have 0 in one port, that means the light are, in a sense, countable. You can.
But we cannot say the phase difference doesn't affect.
Hmm?
I mean the internal or external phase difference is different. This one is you mentioned about the internal phase difference, but if we have external phase
Yeah. I'm talking about even with the external phase difference. Yes, with classical wave, you can arrange such that on one port you have no light, and the other port you have light, right? So that's destructive interference. But when you move your mirror position a little bit, then that you move away from that destructive interference point, and light comes back, right? But what we see here, or what we see here, okay, this is a result. This is a consequence of two physical results. One is the relative phase difference between the two photon states, and the other is one port get completely depleted. Yeah? Okay? So these two physical process, one has a classical analog, but the other one does not. That's what I'm trying to say. The other one does not. Independent of your phase shift, the other one always have 0 on one port. And of course, it's not like always 0 because on detector 1 and detector 2, as a function of time, you see they have the same count. So it's not like this dip is not because you are locking photons in one port. Yeah?
It should.
But
it should go down and up.
No.
Because at the same.
Your raw data from the detectors are the same. Okay? But the coincidence there's 0 coincidence. So that means one port get completely depleted when the other port has signal. And when the other port has signal, this port get completely depleted. And this can happen if and only the photons can be counted. They are like countable entities in the light field. That's what I'm trying to say. Yeah? And if we can manage to do different input states, so instead of 1 and 1, we can do, for example, 2 and 0, and 3 and 1, or 2 and 1, like different combinations. All these combinations, turns out, it will all give you, some of them will not have a dip, but all of them will have different results. It is very sensitive to your input photon states. They all have different signatures. Okay, so the generalized Hall-Mandel experiment all have different signatures depending on your input states. And that just, I think that shows that, so if you are ignorant of the corner optics theory, just by seeing that experimental fact, that by preparing your input state differently, okay, you can have like such dramatic change in your signal. I think that shows the particle natures of light. Okay, because if light does not have the particle nature, or this specific light source does not have the particle nature in it, it only has the wave nature, then what you do at most is just to change the ratio between the two ports, change the intensity ratio between the two ports. And that's not, according to classical theory, that's not going to give you such a dramatic change in your experimental signature. Okay? So that's why I think the Hall-Mandel experiment is the experiment that does shows the particle nature of light. Yeah, you have a question?
I just want I know it's not a cool pair, but what like
You're looking for the bosonic picture?
in gold, in metal, in maybe in critical temperature, under critical temperature, you will have a perfect pair, right? But it's interaction, not
Okay, I think Tom is looking for an explanation for why there are two in one pore and not the other. Okay, it is very tempting to see that, to go with the following picture. So because photons are bosons, so if you have one photon coming here, the other photon coming here, this photon will want to follow this photon. Wherever this photon goes, it will go with it. So if this photon go like this photon will go with it, right? So that's 2, 0. And if this photon go here, this photon will go with it. So that's 0, 2. Is that the physical picture you're looking for?
Yeah.
Okay, that's not true.
I think he mentioned about some interaction.
What?
Interaction picture.
That's he's looking for this bosonic picture, right? This is the one you are thinking about. All right. So like I said, yes, it is very tempting to think that this is what's going on. So, like I said, one photon follow the other photons, right? When this goes here, it follows it there. When this goes through, it follows it to this port. So you always have 2, 0 or 0, 2. If this will be the case, then inputting 2, 0, you will have just 2, 0 or 0, 2, right? Because if they are stick together originally, they will not want to separate. If you go through the math again, so starting with 2, 0, okay, you can do this exercise yourself. You'll find that the output state will have 2, 0, 0, 2, 1, 1, and the 1, 1 does not cancel. So you have all kinds of results. And if you input, for example, 2, 1, right? So just adding one more photons to 1. With that pictures, you will expect 3, 0 and 0, 3. Yeah? If you run this math again, you'll find that that's not the case. You have 0, 3, 0, 2, 2, 1, and 1, 2, and 0, 3. All four will be all there. Okay? So the fact that we have 2, 0 and not the interference term, this is a kind of coincidence. This is like just a very misleading coincidence. Okay? It just so happened that the cross term cancels, and you have only this term left. But with the different input states, generally, you have more terms. Okay? Nevertheless, this does not change the fact that I said that when we have different input states, so photons are supposed to represent the amplitude, right? So if the amplitude are not quantized, does not have this quantized nature, if amplitude can be changed continuously, then at most we're just changing the relative amplitude of the two ports, right? And it should have, maybe a little bit of, if we change, amplitude here a little bit versus here, it shouldn't affect this too much. And it shouldn't affect our correlation measurement too much. That's what we will expect from the classical wave picture. But the quantum, the experimental fact shows us that as we change the amplitude just like a tiny bit, like I said, 2, 1 and 1, 1 give very different result, right? If you have 2, 1 instead of 1, 1, this dip will not be there. It will go up. So you have like dramatic change when you just change the field amplitude just tiny bit, okay? So that shows that the amplitude, the field amplitude, has a quantized nature. And that unit is very, very small. Okay? So I hope this, I'm not very good at explaining this. I didn't do a good job in past semesters, so I hope I'm doing better now. But I hope that this will give you a feel that you know, the quantum nature of light is really there. What is the quantum nature of light? It's in the amplitude. It's not in the mode. It's not in the polarization. It's in the amplitude. When the amplitude change a bit, then like the experimental measurement result could be drastically different. Okay, so that's what I'm trying to get this to. All right, let's take a short break, 5 minutes, and we'll come back to our delay choice experiment.
Simon and Dina have another trip. Alright.
Hmm?
They travel around.
I don't think so.
Yeah, because last time I remember they mentioned they will go to China. Yeah, because this is like near the end.
Yeah,
the
so
semester,
that's why they went to Hong Kong to get the visa.
Oh, okay, I see.
Okay, I didn't know they go to China, but like
Actually, I
I know
don't know
people
visa.
I know people who goes to Hong Kong just to get China visa
Oh, really?
because you cannot get the visa from Taiwan.
Oh, okay, I see.
So like most European can go to Hong Kong without any visa.
Oh, okay.
So they could go there,
So
get the visa, come back.
Oh, okay, I see.
I know that, but
That's the reason.
I don't know whether
Because
Simon and
actually
Vida did that.
Yeah, they did. Because Vida went to Hong Kong first, and then Simon.
I don't know. I thought both went at the same time.
No,
Oh.
they separated out. But I didn't know about the visa requirement.
Because I have some international students friends here.
Oh.
One of them went to Hong Kong for the visa.
Oh, so
China
you
visa.
mean like as long as we go there, then we can like take the visa easily?
No, because
travel visa.
from Taiwan you cannot apply for China visa because there is no.
But if there is the
No, there is no embassy, China embassy in Taiwan.
Oh, really?
Yeah.
Okay.
So you cannot like.
Oh, so
from Pakistan, you cannot apply for Taiwan visa. So I know Pakistani students come here, they apply for in UA or something embassy, Taiwanese embassy for Taiwan visa. Go there, go to the embassy and apply for visa.
Okay.
You understand? Like if there is no embassy in that country of another country, you cannot get visa directly from that country.
Oh.
You have to go to a country which has the embassy to get the visa.
Why not? Why Taiwan don't have?
China say it is its part, so they don't they don't want an embassy in their country.
But they can come to go because they still.
It's not like people from here are banned there.
Okay.
You can go there. You can apply here.
Okay.
Okay, I see that you all have rested. So let's start. Am I starting with 5? Board number 5? I think yes. Anybody remember?
Yeah, 5.
Okay, thanks. All right, 5. So let's start with this. So around 1970s, when in the early stage of quantum optics, people were still wondering, thinking about the nature of light, especially the particle nature of light. Like how does it work? And of course, in the meantime, people were also trying to understand how this like electron work, because they have this interference fringes from the electrons, right? From double slit experiment. So it's a mystery at that time. And John Wheeler, who is the PhD advisor of Richard Feynman, the famous Richard Feynman at Princeton, have a series of thought experiment called delayed choice experiment. And this thought experiment were realized later, but the purpose of that was to test this idea of photon, light as, like a concrete particle traveling around across space-time. Okay, so he used a very drastic. So in his experiment, he used a very drastic light source, which is a remote star. So suppose we have a remote star, and the remote star emits photons, right, in different directions. Let's say 1 at a time, but it could go different directions. So like here and here, different directions. And suppose this, this photon, if it chooses this direction, because now we're trying to test this work, we're trying to work on the assumption that photon is like a solid baseball that travel across space-time, right? So if the photon take this direction, it does not take that direction. Yeah? So either or. All right. And he's saying, okay, now assume that we have Earth right here. So this is Earth. And we receive these photons, right? And suppose there is like a distant galaxy or something, okay? Like a cloud of interstellar dust.
The source is the star, so it's thermal.
Yeah, it doesn't matter. He's trying to say if light is particle, so he's trying to work on the assumption that if light are like particle, like baseball particles, now emit 1 at a time, right? So forget about all the quantum optics that you have learned, because those are not developed at that time. The particle nature of light was it's like an onion. It was discovered gradually through a lot of theoretical debates, theoretical trials and errors, and experimental confirmations, and like a lot of things. It's a combined effort to learn that light indeed has that particle nature. Okay, but I wanna bring you back to the early stage of quantum optics, and let's start with this naive picture, physical picture, that light, like when we talk about particle or wave, right? We know that light could work as wave. That's no problem. Maxwell's told us that. But what if light works as particles? If light was generated as particles, okay, maybe it can be generated as wave or particle, just like, I don't know, yeah, animals, animals could be born with wings and or no wings. So either fly or no fly, not fly, right? So maybe, so like they don't know how this wave particle, how to reconcile this wave particle duality at that time. But suppose light is generated either as wave or a particle. Okay, so let's work based on that assumption and see what will happen. Okay, so let's say if light is generated as a particle and it takes this path and it reaches the Earth. Okay, then we will see in our detection screen, a mark. Yeah. Now, suppose there's a remote interstellar object, and through the gravitational lensing effect, it could bend the light such that it also reach Earth. Okay? What would this do? Well, since it's coming from a different angle, you will likely produce another point, right? So if we have a screen on Earth and we just like wait for the light, for the particle of light to fall from heaven, then we should have different spots, right? And it's just like randomly distributed on the screen. Okay, cool. Now, now he's saying, okay, suppose that the light was generated from the start, maybe like a year ago, and it takes 2 years to travel to Earth, right? So like by the time it finished half its journey, it's already like very far from the start, 1 light year away, okay? So whatever you do here, or whatever happened here, does not change the nature of this particle. It doesn't change its direction. It doesn't change. You shouldn't be able to do anything to it. It's outside of your light cone, per se. Yeah. So at this moment, if we choose to have a different measurement scheme, so instead of just having a screen here, what if we place a few more optics, okay? Such as, for example, mirrors, yeah? Such as mirrors, and we can reflect light. We can steer them from different directions. We can have lots of mirrors and steer them from different directions, and eventually combine them with a beam splitter, right? And then we look. What do we see? Yeah? In principle, if light is a particle that travel in space and time, that travel across space-time, then whatever we do here should not affect its nature, right? So if it's generated as a wave, it remains as a wave. If it's generated as a particle, it remains as particles, right? So if it's a particle, then we should probably expect just one dot, right? Because now we combine the two paths, and that should be it, just like one dot, okay, or one blob. Okay, so let me draw a more realistic. So one blob. Okay. Now, if if light is generated as wave, then this construction should give us not one blob, but a blob with fringes. Right? Okay? What? So I'm saying if light is generated as particle, it should give you like a blob. Okay? And if light is generated as wave, it should give you fringes on top of that blob. Blob? Is blob an English word? Lump. Maybe I should say lump, like a lump, a bump, just like a spot. Okay? All right. So the question now is, would it make any difference to my result if I choose how I measure it? If I choose to measure it without this additional optics, then I see two spots. If I choose to measure with two optics, do I see this or that? Since the photons has left its source long ago, and it will take another year for it to arrive at the detection site, it shouldn't matter what I do with the measurement setup, and the result should always be the same. So if today, I do measurement like this, and the next minute I do measurement I take out the optics, it shouldn't change the result, right? So this is called the delay choice. The choice is in the choice of measurement scheme, okay? Or if this is too much trouble, we could even do this. We could even put a polarizer here, yeah? And we can set them at different settings, right? 1H, 1V, right? And you would expect that if it's particle, then you always see this. But if it's wave, right, you will see this when they have different signs, but you will see the fringes when they have the same sign, the same polarization, right? So just by turning your polarization axis in real time, right? You can alter, like, we are supposed to be able to alter between two different results. But that is only true if it's a wave. But if it's particle, then we should not be able to alter it, right? So no altering or altering, that's the difference between generated as wave or generated as particle. And since the duration was long determined, it shouldn't matter if I choose to do it one way with the same sign or with different sign. It shouldn't matter, okay? But of course, as you expect, when people actually carry out the experiment, it does matter how you measure it. It does matter how you set this, even though the photon was long generated. It does matter.
Can you ever maybe quick because your picture on the mirror is not too clear.
Oh, this is just rerouting the bin to have them combined at the bin splitter.
Yes, I mean.
Oh yeah, sure. This is not a great picture. Let's say this, boom, this, boom. Okay, are you satisfied? All right. So that's a little like puzzle right there from the solid experiment. It appears that the choice we make with our measurement scheme affect our measurement outcome. Instead of the generation, the way how it is generated, like maybe like particle or like a slide, determine the measurement outcome. It seems like our measurement scheme determine the measurement outcome. And that is what this thought experiment is all about. Okay, it is trying to say that, hey, this particle flying across space-time, this picture might not be correct. Because if this will be correct, I will always have the same result. Right? I should not be able to alternate between these two experimental outcome by simply changing my polarizer angle. Yeah? Okay. So this is called a delay choice experiment. There's another version of delay choice experiment that's even more thought-provoking. Okay? And this is an example drawn from cavity QED. So, so this is this example according to Scully, Martin Scully. So suppose you have. So here I'm presenting you two delay choice experiments. So one is, probably more of like a thought experiment, and the other one is pretty realistic in the laboratories. Okay. So suppose you have atomic beam. Okay, and then you use a double slit to split them. Okay, and the particle, the atoms that go through this slit will immediately be captured by a microwave cavity. Okay, so a microwave cavity is basically a copper box. So so you can put this copper box very close to the slit. Okay, when they are still in the near field. So the interference patterns that you see typically are formed in the far field, but in the near field they are still well separated. Okay, so you can do that no problem. Okay, so you just put this close enough, and you can capture particles going through this slit, 100%. Okay, no problem. And in the same way, you do another cavity here. So cavity 1 and cavity 2. Yeah. Now, imagine and at the outlet you have also a small hole, because the microwave is in this direction, so it doesn't matter if you have a hole here, right? So the microwave is in this direction. Okay, so yeah. So here again, you use two other slits to capture it. So the same two other slits to capture it. So just basically sandwich the whole thing. Yeah? And now you put a screen at the far field. Yeah? And atoms going through the first slit, then and the first cavity, end of a slit here will end up propagating like this, and the other atom go through this lower path will propagate like this. Yeah, and supposedly you will have interference fringes. Yeah.
Why you just want to have a two input light? Why you don't?
This is not light. This is atom.
Oh, it's atom.
Yeah.
So we don't have beam splitter we can use.
No. Not in the way that you typically know. Yeah. There are ways to impose mechanical motions to atoms or electrons using light or field like electric fields, and there are like ways to do it. It's in the field of atom optics. So there are things that you can do to them to make the beam splitting or reflecting, like all these operations are possible. Okay, but here we try to restrict ourselves to the most simple, to a simplistic setup. So just using holes to line up the path. Okay, so basically there are two very well defined paths. One path 1, and path 2. Right? There's really no escape from that because they are like sandwiched so close. Yeah? Now, when these are just like empty, like everything is just empty, this is what you will expect to see. Now suppose you have laser lights. It's called Raman laser. So two laser light 1 and light 2. Okay. Together, what they will do is to introduce a transition. Okay, to introduce some gigahertz transition. So we can excite the atoms, basically. We can excite the atoms from the ground to the excited states using these two laser beams. So this is just a technique that people know how to excite the laser when you have like a gigahertz gap, energy gap. Yeah. Now, if we have one particle and we don't know which way it goes, right? By exciting it, okay, it might be here that gets excited, or it might be here that gets excited, right? By exciting it, and then when it go into this cavity, the cavity are tuned to exactly this, the resonance, to be in resonance with this energy gap. Okay, so it is highly likely, and this is the cavity QED part. It is highly likely that almost like 100% likelihood, probability, that the atoms will release this energy as a photon, as a microwave photon, inside the cavity. Okay? Now, when the atom leave the cavity, the photon remain in the cavity, but the atom is gone. Now the atom go through this hole, either this one or this one, right? And then it gets detected on the screen. Okay, so that's basically the story. So let's say if the atoms go through this, and it leaves a part. So if the atom goes through this and it leaves go take path 1. And you leave a photon, microwave photon in the cavity, right? And then it gets to here. And the microwave cavity, the photons are left behind. It is stored in the cavity, bouncing around. Then what do you expect this fringe will change? What? Shift? Okay, shift. Tom says, I expected it to be shifted. What do you think? Now, it is possible for the atoms to go on path 2. Okay? In that case, the photon will be left in cavity 2. Either way, the photon will be left in the cavity when it passes through it. Okay, so this is like this is like averaging data collected after a long time. So after many trials, I shoot atoms one at a time. Boom, 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 boom. I can adjust my photon, my atom beam flux so that the flux is so low that there is only one atom in the entire chamber at one time. Okay, so there's one atom, and the atom can take either this way or this way.
As its baseline goes up,
Huh?
as the spectrum's base goes up,
Shift. So you are.
not shift, like instead of it going all the way down.
Oh, you mean the visibility?
Yeah, the visibility.
You expect the visibility change?
Yes.
Okay. What do you think, Phoenix?
So it's like a spot,
Hmm?
like a single spot.
It goes from this fringes to a single spot. Okay, that's a very creative answer. Okay. So the divergence change, you're saying? You're like, shrink. All right. Okay, that's all good. Let's see. Conceptually, we don't like when if the laser is not turned on, right? The atom is not excited, it's in the ground state. So atom in the ground state. And here atom is in the excited state. And here again atom is in the ground state. Right? So if the laser is not turned on, it will remain in the ground state through the course of its travel, and you will create fringes. That's no problem. We all agree on that, right? So these are basically just like one tiny device that has 2 pinholes. Okay, and you can imagine this as like a box. Okay, and this box has like an opening, optical axis for the laser light, and that's all. Right? Yeah. So this like entire box has 2 holes, 2 through holes, and if the light is not turned on, you see fringes. Now, what if the light is turned on? If the light is turned on, then it is designed in such a way that when the atom must be excited to the excited state. Okay, before it enters the cavity, and when it leaves the cavity, it will return to the ground state, and it will leave a photon in the cavity. Yeah. So in this case, these 2 paths become distinguishable. One path has, at this single trial, this path has a photon on its pathway, right? And it's contained by a cavity. and the other path does not have a photon, right? So these two paths become distinguishable. Even though you are not measuring these photons, it is still conceptually distinguishable or physically distinguishable. And that will result in a washout of your interference fringes, because the which path information now is obtained can be possibly obtained, and so the interference fringes is washed out. Okay. So now the tricky part is the washing out is not surprising, because we know from quantum mechanics, if you somehow label the path, if you can distinguish the path, then your interference, the quantum interference, is gone. So that's not super surprising. Now, what is tricky is you can switch between these two patterns by pressing on your laser light button. Okay. So when the atom is emitted from the source, it's generated already, just like photons are generated from the light already. It already leave the source, right? So you either stay as a particle or it stays as a wave, right? And then now I have not decided whether I want to fire the laser or not until it reached here, right? It reached the entrance of this box. And I decided, okay, now I want to fire a laser. And then I will see that it is possible for the atoms to land on a spot that was previously empty. Okay? And if I don't do this, then it will never land on this spot. So this is another version of delayed choice experiment. Okay? So it seems, in this context, it seems more realistic, how like it makes the point stands out more, that this is kind of strange. Okay? What phase change?
Make the light phase difference. So
the light? You mean this?
You have two phase.
Yeah. Uh-huh.
You excite one phase, and then you go to the cavity.
Yeah.
The light phase didn't change.
The path.
The phase. The path.
Uh-huh.
The path.
The path does not change. No. Yeah. When it's absorbed, because this the Raman process is such that it absorbed one light and then stimulate, emit. Anyway, it does not impart significant mechanical momentums on the atom. It will not change its trajectory by the excitation of the laser. If you have a single beam, yes, that could, in principle, change its direction. But given the divergence that we have, the experimental tolerance that we have here, that is also, that does not change the experimental skin significantly. Okay. So that's not a problem. So here again you see, maybe in quantum mechanical terms, that this choice of measurement schemes changing your experimental outcome is bizarre. What is even more bizarre is is that if you sort your accounts so if you take, so because this is a microwave cavity, right? If photon gets absorbed in the cavity, it will produce some kind of microwave signals, voltage signals. So you can take that voltage signal Okay? You can take that voltage signal, you can collect that voltage signal, and then use it to gate or sort your experiments. Okay? So you can have the light continuously on and the atom source continuously on. Okay? And so sometimes it goes through path 1, sometimes it goes to path 2, path 1, path 2, path 1, path 2, right? And you could, if you do not sort your result, you just collect everything on your screen, then it is a big blob. Okay? It is a big bump without fringes, without structures. But if you sort it, if you sort your count rates and you collect your count rate in 2 groups, okay? When there is a signal in the lower detector, detector 2, which means if there is a signal in detector 2, that means there's a photon in cavity 2. When there is a signal in detector 1, there's a photon in cavity 1, right? If you sort your atom counts on your screen according to the firing of these 2 detectors, then you will see that the interference fringes is resumed. Okay? In 1, so this is detector 1, it'll be exactly like what you had before. But in detector 2, it will be, you have the opposite phase. Opposite phase in terms of the dip, the peak become a dip. Okay, and the dip become a peak.
Can we simply just because we know which hole the light comes,
Mm-hmm.
so it's one hole diffraction. So it's just a one hole diffraction.
One hole diffraction does not give you fringes like this. The single slit diffraction and double slit diffraction are very different. Okay, so this is in the single slit diffraction 0 order peak. Single slit diffraction looks like this. No, this is not this is not what I'm talking about. I'm talking about double slit diffraction pattern being restored. Okay, exactly as before. Exactly as before. The periodicity does not change. Okay, it's just the dip is flipped to the dip is flipped to a peak is flipped to a dip. That's all.
So it's a realized decomposition. It's just a separate red line.
Yeah. So if you do not distinguish particles coming from, if you do not gate your detection, okay? If you, and yeah, Tom has a point. If you gate your detection, that means, oh, it must come from here, right? And then you're supposed to see a single slit diffraction. I get your point. But no, that's not what you see. What you see is double slit diffraction pattern restored, okay? And what's more is that they have opposite phase. The two results have their opposite phase. Okay, maybe I should.
But Tom's doesn't make sense because just by knowing one particles which came from doesn't means like every time it comes through that hole, right? So
well, if you have a signal from here, it must go through this.
yes,
Right.
yeah, at that time it come from there.
Mm-hmm.
But single slit diffraction is not a procedure of like saying only one time it comes. You need multiple time to get the spectrum right.
Yeah.
So, but
But
one time
every
it come
time,
from
every
there,
time you get a spectrum, it always go through this path.
yes.
So you always go through a single slit.
Not a single split result.
It,
But this is not a single slit result. That's what puzzles it in. Okay?
no, but we have means the other slit atoms are also passing to other slits some other time, right? So
How? Some other time, if he had, because now we when it goes through, whether it goes through one or two, it must be excited. You always be
Yes.
excited. So if you go through, this, then you will always be labeled. That it will leave its, it will leave its photons there.
yes.
Is the D1, D2
No,
kind of
I'm saying like we know it come from there doesn't make it's a single slit, right?
Why?
Because at the spectrum it's still like okay either come from here or here. It's still like a double slit, but we just know which slit it come from, right?
I don't know. Anyway, you see how this is thought-provoking? It kind of, upsets you. The result kind of upsets you, okay? That's the purpose of this. That's the purpose we're discussing this.
Yeah. My
Okay,
point.
let me continue because we're running out of time. I understand that you have thoughts and you have, a lot of things to say about this, but just let me finish first because we need to finish this in time. I'm just trying to tell you that what would you expect when this happened? Okay, why does it happen this way? We will discuss it later. Okay, this is what's going to happen. So if you don't sort it, then the two results will add together and then they'll give you this red, featureless bump. But if you sort your counts according to which cavity fires, then you will have two sets of interference fringes. Okay. So this is like, this shows the spirit of the delay choice experiment. Like if this does not feel surprising to you, this does, right? So they are trying, these are both delay choice experiment, and they are trying to show you the same thing. This is more, the thought experiment here is more intricate than this, but nevertheless they serve the same purpose. All right, so what is going on? In fundamental quantum optics, or in fundamental quantum physics, there are a lot of paradox and a lot of puzzles, lots of them, especially in the early stage of the development of quantum mechanics. There are lots of them. And as time goes, a lot of them have been sold out, but there are still some that are not, okay? The remaining one just become more and more subtle. Yeah? You heard about people trying to close loophole of the Bell inequality and this and that, right? They are trying to do a lot of things to solve the subtleties in all these paradox and puzzles, all right? And this is just to demonstrate the nature of such paradox. Okay, now what I want to get to with this lecture is a lot of paradox can be resolved if we articulate the physical process in the language of math. Okay? Here we are trying to discuss it using English. And it is kind of, like you said, oh, you must go through this and then it must see a single slit. Why does it not show a single slit differential pattern? And then it's kind of puzzling, right? And the other person say, oh, no, 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 this can do this and that. And the other person say, no, 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 right? So when we use words, we can easily get into the trap of some blind spots of our thinking process. But if we can articulate our thoughts or the physical process in the language of mathematics, then a lot of things can be resolved. Okay? So this is what we're gonna do. Oh, by the way, so delay choice, right? So this part, by switching on the laser or not, you switch between these two outcomes. So this is the delay choice. This is called a delay choice experiment. Have these additional detectors connected to the microwave cavity and use their signal to gate your detection or to sort or to post-select your detection. Those are sorting, filtering, post-selecting, gating. They are all the same. They are all synonyms. They all mean the same thing. Okay. So using this skin to restore your interference fringes. This is called delay choice quantum eraser. Okay. Delayed choice quantum eraser. Okay. What does it erase? In the delay choice experiment, it seems like the which way information kills our interference signals, right? Just as what happened here, right? When we put this at different polarization, we label the path 1H, 1V, and that kills the interference, right? So this labeling with the laser, with the microwave photon, also kills the interference. So this part is the delay choice experiment, and that's what I want to cover in the second part. In the second part of the lecture, and if we sort our measurement, if we gate our measurement according to the microwave cavity signals, then apparently we can restore the interference signal. If we can restore the interference signal, then it seems that we have erased this, which somehow erased this which path information. Otherwise, we shouldn't be able to restore the signal, right? Because it was the which path information that kills the interference fringes. Now, if we can restore the interference fringes, it seems like the which path information is somehow erased. Okay, that's what the erasing means here. All right. So I just want to be clear with the technical jargons I write down here. Now I want to walk you through this physical process. We want to articulate the physical process in the language of mathematics, so that we can have a clear view of what's going on here. All right. So for the sake of simplicity, I'm gonna label this H, okay, and this V. Yeah? Okay, let me see. Uh-huh. Let's see. Sorry, I'm missing a part of my note. So I cannot do this for this guy. I can nevertheless do this for in your experiment in your optics experiment. There's also this delay choice experiment, and it is constructed in the following way. It's much more simplistic. It's basically a light beam going through a beam splitter and bounce back by two mirrors. So this is a microsecond interferometer. In one path, you put in a polarizer H, and the other path polarizer V. Okay, and here, so these two serve as the delay choice, the so-called delay choice, right? Because if you imagine your photon is like a ball, a baseball that go through the interferometer, then you can, after it was generated by the light source, you can choose to turn your knob in the interferometer, turn your polarizer in the interferometer to decide whether you want to use HV or VV, which measurement scheme you want to use to measure it. Okay, so that's the part of the delay choice, and if you put in a third polarizer here, okay, and this polarizer could be adjusted in different angles, either H or V, or 45 degree in between, okay? And according to, if you do H, then you will still not, okay, so if this is H and V, so this is H and V, you will see no interference patterns. Okay, but if you make this 45 degree, then you will restore the interference pattern by adjusting this. Okay, so this erases the which path information, sort of. This erases the which path information and restore your interference fringes. All right. This is just like, this is, in my opinion, this is not a true delay choice eraser, quantum eraser, but this is to illustrate the math. Okay?
Is it something similar to the Bell effect?
Bell?
Yeah, because at like
No.
45 degree, there shouldn't be anything if you have put like V and H polarizer, right? It should.
No, this could be even understand through the classical wave polarization. Yeah? When you have
It
classical wave,
one way with H and one
yeah,
way with V.
but when you have classical wave, one in H and the other in V, by putting this, you're projecting H and V both to this axis. So the polarization now again is aligned. So you can have interference fringes. Like this can even be, if you have the coherent light going through this setup, you give the same result as a single photon light, no difference. So in a way, this is not like a real quantum experiment, not like that. Okay, this is not a real quantum experiment, but this is a good illustration for the math. Okay, so I'm going to, the reason I'm mentioning this because I'm going to base my math on this. All right, and this is like a much easier construction, and this gives the idea of like delay choice. How does delay choice show in the mathematics? How does the delay choice quantum eraser show in the mathematics? How they work? What's the mathematical machinery that describe these two physical processes? Okay. So I'm going to do that, and for that, I probably will post a note on eLearn. Okay, because my note is based on this. I forgot to get my note. I get a note for that. All right, so let me just do this. So my light field, the quantum state of my light is, so this is K1, this path K1, and this path K2. Okay, so K1 and K2 are now labeled, or you can say entangled. Okay, with the polarizer. Yeah. So if you have two states and the two states, if you have a superposition of two states and the two states are separately labeled, then this is basically an entangled state. Okay. And what this does is if you take a measurement, you take the probability, right? Measurement. Then this will give you okay. This will give you 4 terms. Without the labeling, by the way, these are not orthogonal states. They are just two. They are basically just two fields. They come from different paths, but they overlap at the detector. So cosine, this is, you can say that this is cosine kx plus omega t, and this is cosine kx minus omega t, and k here. K here represent the angle. So if they are not parallel, if they have an angle like this, they can produce fringes. And then this K represent their projection on the vertical direction, and the plus minus sign means they are coming from different directions. They are like counterpropagating. Okay, so these are, so I'm just saying that this is not orthogonal states. So you will have non-zero terms in the cross terms, right? And these are the self terms, okay? Now the cross terms, I use a red bracket to show it. Now you see, if with labeling the cross terms, the interference terms now have this thing there, right? So you can say that in the language of entanglement, you can say it is the two paths are now entangled to the environment. The polarizers are the environment, okay? Except here you can monitor the environment with the full knowledge. So your environment, if your environment is simple enough, you can monitor its quantum state with the full knowledge, no problem. Okay, so say this is H and this is V, and if the environmental states are completely orthogonal, then this is 0, and that will kill your interference fringes. Yeah, but if they are partially overlapped, so if this is like not V but 45 degree, okay, if they are partially overlapped, if this is not V but some kind of angle phi, then this will not be 0. So you will still have some value in your in your cross terms, and that will still give you some fringes, but the visibility of course is low. Okay, so we know that. Now I want to use you want to use a slightly different language to describe this. Oh, sorry, this is supposed to be 7, right? Because that was 6. So now we do it.
Shouldn't we add the beam splitter into it before calculating the probability?
No, because here we are. Here, when I am not expressing, well, there are two reasons I don't need to invoke the beam splitter operator. Number one is the beam splitter acting on the coherent state has exactly the same result as the classical wave. As the beam splitter working on the classical wave, you just simply divide your amplitude by 2 and maybe attach a phase or something, okay? That's one. And here we're talking about coherent state, yeah? Number 2, K1 and K2 are path that labels the path that go through H or that go through V. That's all. But they are both like at the output port. So they are already in the output port. I am not. You see, I'm expressing this as the output. So out. I'm expressing this as the output. So the output has 2 states, and the 2 states are separately labeled. Okay, that's what I'm trying to express with this. Okay, now I want to use a slightly different language. It's called a density matrix. Because in this language, we see a slightly different face of this whole business, and I believe that's important. Okay, so density matrix is pretty straightforward, but it's kind of tedious. So you just have to take this whole expression and flip it, K1 H K2 V. Yeah. Okay. And then just expand it turn by turn. So at the end, you will see okay. Okay. So density matrix has basically two parts: the diagonal parts and off-diagonal parts. Okay. Let me just label this with red. They have two parts. Okay. This thing, these are the diagonal parts. Oh no, I'm sorry. No, wrong. Sorry. If the density matrix is in the base of K1, K2, H, and V, then this will be the diagonal parts, and these will be the off-diagonal parts. But if the density matrix is in the base of X, okay, so K1 is basically a series of values, and each value is this function at x1, x2, x3, right? If density matrix is in the X basis, then all of them contribute to both the diagonal and out of diagonal. Okay? So this is not right. All of them contribute to the diagonal and off diagonal. Okay? However, your measurement result is read off, however base it is written. Your measurement result is read off from the diagonal element. Yeah? Which is this. This is your measurement result, probability. That is read off from your it is not hard to see. If you take this, if you take this as a series of values, and this as a series of values, and you do a tensor product, then the diagonal element will be the same as the inner product. Okay? So this is the probability. This is your measurement result, the diagonal terms. Therefore, the diagonal terms have contribution from all four of them, right? And all four of them are all four terms are the diagonal terms from this, as you could easily see. Yeah? So these are the diagonal terms. This is diagonal terms from this matrix, and this is the diagonal terms from this matrix. Okay? Now, you see the interference part, the interference signal the interference fringe that you have in the probability comes from these two matrices. Yeah? Because I'm just like tracing where this term come from, where that term come from, right? It comes from this matrix. Now I want to bring to your attention that this matrix is not zero. Because this is not a dot product, this is a tensor product. Okay? when you have a dot product, if you label H as 1, 0 and V as 0, 1, right? A dot product will give you is this right? No. A dot product is 1, 1, 0, right?
Yeah.
This will give you 0. Okay? But a tensor product will give you 0, 1, 0. Yeah? Okay? A tensor product is not 0. Okay? So what I'm trying to tell you is in the density matrix formalism, you can see clearly that the term responsible for the interference fringes remains here. They are here. They are not 0. They are not like just gone. Here they are erased simply by the fact that these two are the orthogonal bases. But these are not. They are not. They are here. Okay, so they are present in the overall density matrix. Okay, that's important. But what is going on with this thing, the disappearance? What is going on with the disappearance of interference fringes is when we take a measurement, right? Our detector cannot distinguish between polarization H or polarization V, right? You just take values, photon counts. It doesn't matter if the photon has H polarization or V polarization, it all count as 1, right? One photon count as 1. Doesn't matter what polarization it has. It does not distinguish polarization. Therefore, in our measurement, we are through our measurement scheme does not allow us to distinguish H or V. So what we have is not the full matrix, full density matrix. What we have is the reduced density matrix. Why does it call reduced density matrix? Because we leave out the information. We leave out the information of H and V. We don't know the incoming photon, the polarization of the incoming photon, whether it is H or V, we do not know. Okay, we leave out that. So this is called reduced density matrix, and the reduced density matrix is obtained from the original density matrix through an operation called the partial trace. Okay, partial trace. And you need to specify what degree of freedom you want to trace out. Okay, so here for us it is polarization. So we want to trace out the polarization, and how does that work? That means you need to sum over all the polarization state. So it's basically a trace according to the polarization state. So it's basically a trace that you would do if you just have a density matrix of the polarization state, if that makes sense to you. If you have a small density matrix 2 by 2, right? Like this, it just has the polarization state, and you do a trace. That's you sum the diagonal terms, right? And mathematically, it is expressed as this. You're basically try to like squeeze it with the two bases H and V, and you sum them. Okay, this is equivalent to this operation, summing the diagonals. Okay, so if you do this, then you will see that you are left, so this term is gone, this term is gone, right? And you're left with these two terms. Yep. So this is what our measurement scheme give us, because we do not have the ability to separate, to distinguish result between H and V polarization. So we have basically an average of all the results. Okay, and this is what the density matrix that we have. And you can see that in this density matrix, we only have the terms that make the DC signal. Yeah, we only have the term that makes the DC signal. Therefore, in the diagonal elements of this density, of this reduced density matrix, there's no interference fringes. Yeah. So in the language of density matrix, this is how the story is told. Okay. Now, this is the delay. This machinery describes the delay choice experiment. The delay choice is basically a labeling of path. Okay, a labeling of path. And when you label the path, but your detection scheme cannot your detection scheme cannot distinguish your environmental your labeling environmental states, then you have an average, and the average will sort of wash away the interference, the density matrix that carries the interference terms, interference features, and then you're left with a featureless probability distribution. Yeah. So this is the delay choice. This is how the delay choice is expressed in the quantum mechanical language. Now, let's go to the eraser. Okay. So the eraser is basically so in our construction, the eraser is a polarizer that is at 45 degrees between H and V. Yeah? But so H is now this, and V is now H is minus V, right? Okay, but this can be cast into a more general terms. So this is B. This can be cast out into more general terms. You can say that my eraser is a process that casts this into a symmetric subset. Okay, let me put this way. So this transformation you can see that this is A is B is B is okay, so VH V plus H V minus H. Okay, so this is how A and B are expressed in terms of V and H. Okay, so so instead of this, very specific implementations of polarizer, we can generalize this formalism and say, eraser is the process of sorting your measurement into the symmetric set and the antisymmetric set. Okay, so it is a process that sorts your measurement or sorting your measurement into two subsets. One is symmetric, and the other is antisymmetric. Yeah, that I will give an additional on eLearn. Okay, but just remember this is the underlying. This is the idea. You sort your measurement result into a symmetric set and an antisymmetric set. Okay. So instead of, we don't have the direct information of the environmental states. But if we could use a method to sort our measurement into symmetric and antisymmetric set according to the environmental states, then we could possibly restore the interference fringes. And now we want to see how that mechanism works here. Okay? So coming they are really okay. So if I let me see. Okay. All right. So if I write this in terms of A and B, and this in terms of A and B, right? Let me give me a second. Yeah. Let me just cheat a little bit, okay? Because I got my labeling wrong here, so I'm just gonna call this H and this V, okay? Without loss of generality, I call this H and this V, so that H will be here and V will be here. Okay? Okay. I can of course write everything in the correct way, but then I won't be able to follow my note, and that's extra time. So I don't want to do that. But you can see now I'm basically just exchanging my labels. Okay? So this is H plus V, and this is H minus V. Okay? Yeah? Or I can say, if I just have you know what? I think it will be, I think it would be better if I just do this instead. Okay, I can remain my notation, but I will have A and B like this. Okay. So this works, right? Does this work? No. HV.
No, A and B will be opposite, right?
B will be opposite.
A will be the upper one and B will be the lower one.
Oh, yes, thank you. Yeah? All right, great. So this fixes everything. All right? Okay, so everything's consistent. Great, awesome. All right, so if I write my H and V in terms of A and B, then I'm just gonna write the result, but wow, you want to start with this. Okay, let me just write it here. This will become K1, K2, A, K1 minus K2, B. Okay? All right, so my state is written as that in the new base, A and B. And my density matrix now look a bit more complicated. Okay, that's the first one. Yeah? So these are all pretty straightforward, but you need to be patient. That's the thing about quantum optics. There's just so many results that looks very complicated, but if you are patient and you just write them out, you'll find that they are actually quite simple. They are not as complicated as they look, because magically things cancels with each other, and things arrange themselves into symmetric and anti-symmetric forms. That's the beauty of quantum optics. So there's a lot of order in it. Okay, so it looks like this. Yeah. This is just this in the new base.
I would say this reparameterization look much like the output of beam splitter that we saw before. Right?
Sorry?
This new bases look more like the output of beam splitter that we saw before in the HOM experiment.
Home and Dow?
Yeah, we have the output of beam splitter look like when we are changing to this basis.
Well, there I use I and I and one, but one and minus one. That is your suggestion. But no, this is different thing, because there you have like a very strict rules about the choices, and I and one and minus one, those are just possibilities. But here, the symmetric, you see this is the symmetric and anti-symmetric ordering. These are from the structure itself. This has nothing to do with our this is inherited from here. Okay, so like the physical origin is different. All right. So where do we go with this? So 9, and this will be the last one. Where do we go with this? Well, there are two ways we can go about this. But so there are two ways we can calculate what happened with the projective measurement. The projective measurement is the measurement of according to certain results. So that's basically sorting. Okay? So you have two types of detector. Okay? One detector detects A or B. So somehow one detector can distinguish. It cannot do H and V, but it can do A and B. Okay, so somehow this is not sensitive to the H and V state, but it is sensitive to their parity. So if you have like a H plus V state or H minus V state, this can tell. Okay? All right, so that's this. Okay? So if we can have a projective measurement, and this, of course, measure the interference, right? So projective measurement means you are sorting your measurement result according to your result here. Okay, so it's like projecting. It's like projecting your state to A or projecting your state to B. Okay, and then you get your result. Okay, and there are two ways to calculate the projected density matrix. I'm gonna go with the easy way, okay, because this is less trouble. The easy way is to start with the wave vector, to start with the state. The hard way is to start with the full density matrix, like what we have here. And I will later show you how, like, I'll give you a formula how to do that, but just a lot of, it's kind of tedious, so I don't want to do it. All right, so the projective measurement is have a projective operator acting on your state, okay?
There's a small mistake in the density. The last term should be minus. Means K minus K, yeah, that.
Here?
Yes.
Okay, thanks. Okay, thank you. Projective measurement it has is represented by this projective operator. Okay, and projective operator, you can get that by simply knowing that how do you know what is the probability of your state, after the measurement fall on a certain eigenvalue, right? You take the inner product between the eigenstate and your vector and your wave function, right? So here is the same. The projected state, the state of your interest, the inner product, that is your probability amplitude, okay? And once you project it to that state, and you remain in that state, okay? So this is the amplitude. From this, you can see that I can rearrange this to here to be like this. Yeah? And I can take this as my this is my projection operator. Okay? All right. So my projected state is the projection operator working on that, and this will give me I erase it, but this will give me this. Okay? Yep. And now, is this state normalized? Before the projection, it is normalized. I know. Okay? Before the state was, so let me just probably write it down here. It is okay. So this is a normalized state, right? No problem. This is 1. But the projected state, is it normalized? This is square, right? And this is 1 plus 1. Yeah? So, sorry, this is 4. So this is 1/2. So this is now normalized. Yeah? So usually you want, when after the projection, you want to normalize it. So let's redefine the projected state as after the projection, you normalize it. Just like we will normalize with a normal wave function. You just take the inner product and then square root of it. Okay? So this is just normalization. And now the projected operator, the density matrix of the projected state is also called the projected operator, is, as you can see, so that's just this and that. Oh, by the way, there's one property about a projection operator. If you project it twice, you return to itself. I think that's pretty obvious. If you just like double this, do it twice. Inner product of A and A is 1. Okay, so that just give back to itself, right? Sorry. Yeah. That's just this, right? Okay. And so we have 2 from here, and projection operator acting on this is this. Yep. Hold on. Oh, sorry. 4 here. Okay. All right. All right. Almost done. Almost done. And you see that this give you Yeah? You see that this gives you, in a sense, a disentanglement. In a sense, a disentanglement. You have now the cross turn kind of detached to the polarization state, right? You see the cross turn originally in this space. The cross turn was attached to the polarization state. Yeah? The cross turn was attached to the polarization state. Now the interference of the cross turn, the interference which give you the interference fringes, now is disattached to the polarization state. Okay? Yeah? So here, when you make a measurement, it doesn't, if you can, I mean, this part simply doesn't really matter because now you already sort, in your measurement scheme, you already sort all your measurement according to this result, right? So you can, of course, you can take a trace, right? You can take a trace just like what we do here. We take a trace of the polarization. Now, but the trace is just AA, right? This term will remain. Okay, so this term. So when we take a partial trace, now when we take a partial trace now, yeah, we are left with this. The interference terms remain. So the diagonal terms of the reduced density matrix now will contain the interference fringes.
But we could have also got the same from taking the partial trace of the
B.
No, means in the other row, the big matrix. If you take partial trace with respect to state A, we will still get it directly, right, without going into any projections.
But there, the partial trace will be A and B.
But partial
right?
trace, we can say what we are tracing over.
No. You can trace the system, but you cannot trace a state. If you take a partial trace at this level, that's what we're talking about, right? If you take the partial trace at this level, that's what you want to do. Partial trace, I do a partial trace with this, right? But instead of H and V, I do A and B. Then this will be this.
But partial trace means like we are tracing over something, and we can define what that we are tracing over. If you
can only define the system you want to trace over. And the system here that we're tracing over in this example is the polarization system, is the polarizer state.
Yes.
Okay, and when we do this, we're doing either AABB or HHVV, right? And since AABB here is now disattached or disentangled from your interference fringes, and this is only AA, no BB. So this states. But if you do it here, then you will have this and this.
Means if you take partial trace like that, But we can define it as such as we are taking a system, right? But
Sorry?
it's a different, means it's not, we'll get not.
If you don't do projection measurement,
Yes, we are doing projection, but instead of defining like this projection measurement, we can directly define in the partial trace.
no, you cannot. You cannot do projection partial trace.
You mean
You cannot just like
Because-
do this. You cannot just do this.
It's like we can define the basis that we are taking the trace, right?
No, yes, you can define the basis where you're taking, but you need to do it both. You need to do both of them, like all of them. You need to run through both A and B. So if you have both A and B in your system, then you will have like a lot more turns than what you have here. Here we have only A. You must go through the projection measurement. Partial trace and projection measurement, they are different things. They're, separated. There's no such thing as projected partial. That's just mathematical. That the thing that you're talking about, the projected, if I just keep this, like if I just do this, that is just mathematical operation. It doesn't mean anything. It does not have any physical meaning. Okay? The projection measurement that we try to invoke here and the partial trace, these are all correspond to our measurement process. Okay, so our measurement process restrict what kind of mathematical operation we can do to the states or the density matrix. All right? All right, so what I'm trying to get to is, you see that the projection measurement effectively disentangled your interference fringe turns or cross turns from the polarization system, from the polarizer state. Okay? And that's what gives you back your which way signal. So in the sense, the which way, the which path, the label is now being lifted off by the projection measurement. You can say that. And that's how the eraser work. Okay? So still the story is consistent. The which way information, the which path information does destroy your interference signal. The only way to restore your interference signal is you lift off, you kind of remove, you kind of break the labeling. You lift off the labeling from the cross turns. All right, so that's everything for today's lecture, and it's incredibly late. All right, so thank you for your patience. Next, this is our last corner optics lecture, and our next one will be also the last spin lecture. And then after that, we will do 2 lectures on the bonus lab, the Deutsch algorithm. And then we're done with all the lectures. So we have 3 lectures left. All right, so this is the last optics lecture. I hope you enjoy it. It's very long, but I hope that this is informative. And yes, I will post a handwritten derivation like this for Scarlett's delay choice experiment. It's actually published in Science, so I will probably attach that paper too for your information. All right, so quiz time. Bonus points, great. But this is a little, so I want you to think carefully about the question I'm asking here, all right? This could be tricky. So just a warning ahead of one is quantum coherence lost by forming an entangled state. Okay? Is interference signal loss by forming an entangled state? Okay, all right. So let's move. Get up and stand by your answer. Hurry. Go, go, go. Get up, Phoenix. Move. Everybody, move, please. I need you to stand in line so I can move on. Please move. Thank you. Everybody move forward to the board. Just pick an answer and stand behind it so I can move on. All right? Don't try to delay
What's meant by
the countdown.
Can you explain the question?
Okay.
Give us an example.
Is quantum interference?
No, the first one.
Yeah.
Yes.
Is quantum interference of the light? Is the quantum coherence of the light field? Okay, or the system, or maybe I don't know if this will help. If I use general terms, if quantum coherence of system A lost by forming an entanglement state with the system B, does that help? Or is quantum coherence lost? Is quantum coherence of in the momentum state of the light field lost by forming an entangled state with the polarized state?
Quality loss means loss or
Huh?
means,
Lost, gone, zero.
oh, zero.
Okay, okay, great. We have everybody sitting on one line. You are all choosing no. Great, good. All right. All right. Let's discuss. Three of you. I'm tired. I'm sick today. So three of you will discuss, and then you all start with the magical sentence. You are wrong. Okay.
How you are here?
Why are you here? You're wrong. Yes. Okay. Start. Let's do a 1 minute discussion.
It's actually based on the hint. If you give it the hint about, for example, momentum moderation. So
Does
they
it
are
relate to
not
the
present.
final? You write a lot of density matrix.
Yeah, I write a lot of density matrix. That's correct.
Does it relate to?
I don't know. You have to ask Nen. I know nothing.
That's what I don't understand. What do you think quantum coherence in this case means?
Not very clear.
Yeah, that's the problem.
And that's
Like interference signal, when you say we can understand, okay, in this case, like,
okay. I'll give you a hint.
Yeah.
Every question I ask can be formulated. Okay? That means everything I write on the board can be translated into mathematical formulation, which also means every word corresponds to a mathematical entity. Okay? Remember I told you that when we articulate physics in terms of mathematical forms, there a lot of paradoxes and puzzles are resolved. Okay? We need to like make it well defined what we mean by writing it down mathematically, right? So every question I ask you has a corresponding mathematical description in it. Okay? So that would be a hint. Don't know if you get it, but that'll be the only hint I can give you. Well, I don't hear much discussion. It's more like, okay, we don't know what to do, and we're just gonna wait here till.
I just remember you have told him.
Don't talk to me. Don't talk to your.
Well, you
Talk to
told,
them.
erase experiment for polarization. You told some kind of.
Don't look at me. I'm not here. Okay.
What is corner coherence in that case mean? What can be measured? Like how to get the corner coherence? In this last case that you explained, how do you forget entanglement? How do you say this is a corner coherence in that case?
Which
You need to know what.
I think you have asked a question about mixed picture, and you should say in coherence. We use coherence, right? We don't need to
That's coherent,
care,
right? It's the
care
right.
about it.
That's the light source.
All right, 30 seconds.
That's not very light.
You are all wrong. Wrong, wrong, wrong.
Yes.
Very wrong.
I think we don't have any more.
You don't what?
We don't have any more discussion.
You don't have any more questions?
Discussion.
Discussion. Oh, okay.
Because we,
All right, so we're wasting our time. All right, cool. Fine. Anybody want to switch since you're all wrong? Yeah? Switch?
we keep in the same line.
Anybody? 3, count down. 3, 2, 1, switch? No? No switch? All right. Is quantum coherence lost by forming an entangled state? Answer is no. Okay. Most far. Okay. Is interference signal lost by forming an entangled state? All right. So let's do again. Shuffle, shuffle, shuffle. Shuffle, shuffle, shuffle.
It's a tricky question.
Do you say it's tricky? All right. Come on. Line up. No, yes, yes, no. No, yes, yes, no.
Can it be any entanglement or some particular entanglement will lose it? It's any type of, like, you can form in so many different ways. If some ways it is lost, some ways we don't know.
You always have lost.
Always.
I mean, okay, here I mean lost at any degree, okay?
Oh, so you mean
All my questions are qualitative, not quantitative. I don't distinguish A from 6. It's basically +1 or -1, 0 or 1. It's all quantitative. Okay, so don't overthink it. Try to think of the the nominal case, for the nominal case. Don't try to think about like very particular arrangement, All right, so yes or no, yes or no, no or yes. Are you bosons? Gosh. I don't think you have your own thoughts. All right. Okay. Okay. I'm just gonna bear with you. You will discuss with me, and you guys will discuss together. All right. Go on. You're wrong. You're very wrong.
I think in some
Explain yourself.
like are
Because I remember
entangling
when you
these
run,
signals such
you
that
have the
we know which signal will
the
come
pure
from, then the interference signal is
your
wrong, right?
estimation is
Sorry.
Losing from
uh,
this data is for
What? Say again?
I'm not sure.
That doesn't
Yeah,
happen.
that's why
But-
you're
but-
wrong.
there's no another polarizer we measure is no free.
But because at beginning, for example, you start from
No.
We have
This,
cross term.
okay,
He's telling
you
that
start from the basis
if
like
we
V and
untangle this
H right,
state,
and then you
means
just change the
now like
base
we
into
have this polarizer on,
dB
but
A
we
and
are
B,
using
Mhm.
45 degree.
and you establish another
So we'll have
entanglement
difference,
for
right?
Yeah.
V and H.
But now
Mhm.
And,
here we are entangling
In your
with,
projection,
here
I mean
we
the
are
result
using some
show
entanglement. I think here we are entangling these two things. Then put in
interference
the filter
term
and convert.
just
At that time
reappear.
we still have this.
So the answer is no,
So
according to what you said. It's not lost.
No, it's reappear, which means before
Uh-huh.
it's lost as some
So
I think like here we are making the case like even at like
it's like for
we are
example
making the distinction if you are
okay,
entangled like
you have
the state reaching
before the interference is okay.
Forming
For example, you have
you say
some state is like superpositional. Sorry, entanglement. Okay.
we are entangling these two
B
lights
and
too.
X-ray.
So for example
And
like
was
individually we have like this one and
and
this one.
by like
This is like
Mm-hmm.
K1,
I mean,
K2.
Yeah.
in your
Keep trying.
then
But
estimations
when
you
you're
have
just going to bring later, we are
the-
just adding
the
it.
cross term
Or
with
like the density matrix, we'll take the tensor product, we'll
stick
have
with the
HV,
interference part is maybe
H,
K1 and K2.
and VB. So there is coefficient of that. We'll only look at coefficient of
I
the
mean this one
cross term, that's alright.
maybe
But when we are entangling,
and
we are
and some other term maybe this one.
this is like
Something else,
the
but
general
I'm not
so we can
exactly
entangle in some
remember,
ways
but I
like
mean,
okay we'll only have
because
these
when you
no not these we
I
can
mean,
entangle
this term will go to
okay if
zero.
it's maximally entangled we can write
So,
it okay this one or we
but
can entangle
I
like
mean,
this so we'll only
we
have
can,
distance
which means
so we just have to
the
see
interference
its
can be
coefficient.
lost by forming
Then
an
if you
entangled
compare it to the
state with
45
another,
degree
but
thing
it's
means
by
into
eraser,
this was
the electron
XL,
eraser, we can just
oh,
make it reappear.
and the
Okay.
terms,
So is the answer no or
I
yes?
think,
Yes,
oh,
So it's lost.
yes,
not
But just
all
say that you
details
can
of the
reappear.
will be there. So
yes, but when we
I
do
think
the
it-
post
we will get
selection,
Okay.
it will reappear, but before that it can lose.
Oh, I see. Okay, that maybe makes sense. I'm not so sure, but I still think you're wrong. Okay, thank you very much. All right, so line up. Anybody want to switch answers? Do we need another round of discussion? Are we pretty much done? Are you pretty confident with your answers? Are you? Okay. Well, in that case, I would say you're right. Congratulations. All right, so interference signals involve a measurement, okay? And the measurement depends on how you measure it, right? Projection measurement involved or not. If no, then entangled state will certainly kill your interference signal. If projection measurement is involved, then you can restore the measurement entangled signal. Okay.
And how about the
This
first
is
question?
not this is this is not a physical property. This is just your measurement outcome. This is a physical property, and that physical property is there always. Whether it is manifested as interference signal or not, that's another business, but it's always there. I write down, when I write the probability density, when I write the probability using the wave vector, right? You can see the interference is lost, right? But because that is because taking the probability, that action is represent measurement. But in the density matrix, this process is clear, more clearly mapped out, right? In the density matrix, you have a clear distinction between where the coherence terms are, and when you take the measurement, what the density matrix become, right? So you compare not apple and orange, but apple and apple, just with and without measurement, right? So you see, the density matrix, the quantum coherence is in the density matrix, but after the action of measurement, which is partial trace, that part of the information gets lost, so you don't have interference signals, unless you invoke projective measurement. Okay? Okay, great. So I think you all get this idea. And that's the purpose of the lecture. Thank you very much. Congratulations.